Okay, let's go ahead and do our concept review for simple harmonic motion. This one's going to be super short because there really wasn't a lot of content related to this. So where are my tools? I need my tools. I need my laser pointer. There we go. So for simple harmonic motion to occur, a net restoring force has to be acting on the object. Right, so any object that's governed by a restoring force will undergo simple harmonic motion. Now what a restoring force is, it's a force that returns an object to some equilibrium position, and it also has to be proportional in magnitude to the object's displacement from the equilibrium. So if we have an object at the equilibrium point, the further you pull it away from equilibrium, the greater the force's magnitude has to get. Right? And if we were to pull it the other way, the force would increase proportionally as well, but in the opposite direction, right? Because if the displacement is negative, for example, the force would have to be positive to push it back. The two main examples we looked at were a spring and a pendulum. So in the case of a spring, right, the net force is just going to be the spring force, which is this. And it's pretty easy to see why this is a restoring force, right? Because the force is proportional to the displacement of the spring. Here, K is just a constant. We saw that the period of a spring, right, this was an equation that was given, that we used. It depends on the mass and the spring constant of the spring. Notice that the amplitude is not part of this equation, right? It's just the mass that's attached to the spring and the spring constant of the spring. So this was for a mass spring oscillator. Maybe I should actually change it. Instead of just writing spring, let's call it what it is. So this is for a mass, ooh, that's ugly. This is for a mass spring oscillator. There we go. And highlight. Gorgeous. All right, and the pendulum, that was the other example we saw. So a pendulum, the period is going to look like this. And it's important to note that a pendulum is really only a simple harmonic oscillator when the amplitude is small. When you pull a pendulum back really far from equilibrium, it will stop behaving like a simple harmonic oscillator, and this equation will not work as well. And I want to take a minute to just talk about why a pendulum is a simple harmonic oscillator, because we didn't really address it. In class. I just kind of told you that it was and gave you this equation. So I want to quickly summarize that. And if you struggle to follow this, it's really not a huge deal. But for those of you that are curious, I think it's worth diving in. So let's take this pendulum, and if we pull it back, the forces are going to be gravity down and tension this way. And if the oscillation is small, then this component of gravity is going to be pretty much equal to the tension force. And we're going to have one more component of gravity left over. And the reason that we're assuming that these are the same is because if the angle is small, we can pretty much treat the pendulum bob as though it's just moving back and forth horizontally. We don't really have to think about the up and down motion. So with that being said, we can assume that the net force is going to be equal to mg sine theta, right? It's going to be sine theta because theta is, we're defining it as this angle right here, which is the same as this angle here. So the net force is mg sine theta. Well, notice that this isn't, it's not easy to see why this is a restoring force. But with a little bit of work, we can see that it is. So for instance here, if this is the length of the string, then this distance here is L sine theta. And if we sub in for sine theta, because we can see that sine theta is actually going to be equal to delta x over L. And if I plug that in here, well, I get this equation. And notice that m is constant, g is constant, L is constant. So we have this equation that the magnitude of the force only depends on delta x. And delta x is the distance from equilibrium. So this does meet our requirements of a restoring force, right? The force will always pull the object back towards equilibrium. and it's also going to be proportional in magnitude to the displacement from equilibrium. All right, hope this was helpful.